Thank you to the organizer for the invitation. It's really a pleasure to be here. So I'm going to try to describe you the kind of status of where we are today in astrophysics, or more especially in cosmology. And I will try to show you what kind of problem we are faced and what kind of big challenges in the future, especially in the space project Euclid. So the topic of my talk will be, first I will describe the kind of systematics, the kind of problem we have to, uncertainty we have to face and how to solve them. Then I will more give you some details about what kind of data we have today and what kind of data we will have tomorrow in different kind of projects. And I will finish by one specific project, which is a Euclid space mission in which I'm deeply involved. And I will try to describe you two kinds of problems we are addressing in this big project. So the situation today in cosmology is very interesting. Certainly, as everybody knows that we have cosmological models, which is fantastic to explain the data we have. We can explain what you call the cosmic microwave background. We can explain the lensing effect. You can explain the detection of gravitational waves. You can explain the observation of supernovae. Everything is very well explained with this model. But when you look at the parameter of the model, then what we have is at the end we have budget energy where 95% of the energy is unknown. Part is about dark matter, and the other part, which is dark energy. Both these concepts are clearly not completely understood, and the big challenges in cosmology today is to explain both dark matter and dark energy. And so the model we have, certainly everybody knows that. We believe that there is a Big Bang. So the Big Bang is not an observation, it's a model. And what you observe is the light, which is when the universe becomes transparent after the inflammation period. The universe becomes cold enough so the light can escape. And 300,000 later, after the Big Bang, we can see the first light of the universe. And it has been observed recently by the Planck project. And after the gravity starts to play his role, and then there is the evolution of the gravity, and the matter start to gather and collapse, and then we have cluster of galaxies and stars and everything. And then we are here today in this room, and we can discuss it's 30 billion later. So the model works very well, but we have to understand what's exactly the physics behind. Is the gravity really working as we believe it works? And that's the kind of challenge we want to solve. So we want to try to observe the galaxies at different redshifts, at different distance, in order to see how the gravity is working and how it's working during time. That's the whole idea. So to do this, we collect some data from the sky. Everybody has seen already a telescope, right? So we can collect data from the sky. And the first source of uncertainty when we do this observation is what you call noise, just any stochastic process. And we can try to collect more data, and we try to also to have better instruments, better detector, larger telescopes. And starting, I will say, around the year 2000, we have a lot of data available. And then there is what you call the virtual observatory, which took place, where all the tools to manipulate the data through the web have been developed and provided to the community. So people could really play with some software to overlap observation from one instrument to some observation to another instrument. And this is the whole concept of virtual observatory. In the same period, we have also understood that statistics, mathematics, signal processing could really help a lot also to improve the quality of our analysis of the data. And then there is this new field which did emerge, which is called astrostatistics. And the idea was to gather people from mathematics and from cosmology or astrophysics in order to design new algorithms and to better understand the error bars, the estimator, and everything. And now we have some kind of new organization like the International Astrostatistics Association. And you have also a US organization, and there is also some kind of joint lab, like in US, there are several joint labs which include statisticians, people from math or signal processing, and people from astrophysics. And in Europe, there are two labs very similar. One is at Imperial College, and the other one is at CEA, the lab I'm leading. So when we had more data, better statistical tools, then we can reduce the uncertainty due to stochastic processes. So we shrink the stochastic process, and what remains is what we call systematics. Okay, so imagine that you have large error bars, and you shrink your error bar, so you have several times an observation of the same process, and when you can have is some differences, and these differences are related to systematics, something we didn't understand in the data. And one of the biggest examples of this kind of systematics which appeared was certainly the discovery, or the wrong discovery, of primordial gravitational wave in 2014. The BICEP team did claim to have discovered for the first time primordial gravitational waves, and they were showing this plot, which is here. Here in black you have the data, and here is a signal which is coming from what you call reclancing. I will come back to this later. And here's the signal if there is no gravitational waves, and here's the signal with lancing and gravitational waves. So clearly, the data were completely supporting the concept of gravitational waves, but later the Planck projects have shown that what was claimed as a signature gravitational wave, in fact, was just dust in our own galaxies, which was emitted a signal which was not properly removed from the data. So it was really an artifact of the processing, or more, it's not really an artifact, it's something we didn't understand in the dust emission of our own galaxies, which led a signal, a residual signal, and then this was interpreted as a signature of gravitational waves. So just to explain you how difficult it is to claim a discovery and how we have to be very careful to any small feature that could remain in the data. More recently, there is also the Planck data. And this is a very interesting plot that my colleague in Zurich did. They compare two different experiments and how we can compare the quality of the cosmological parameter we are derived from one experiment to the quality of the estimator from a previous experiment. And we can assume that we will improve the quality if you have better sensitivity or larger observation of the sky. So there is something which is quite expected from better data, because we know that the noise will be smaller than you expect to have a smaller uncertainty on your cosmological parameters. So there is something you can expect, and when you get the result from two experiments, then you can compare the difference, and you can separate the difference in something which is expected and something which is quite surprised. So the difference is in a box, and what is surprised is a blue one, which is not expected by just the stochastic process, which is more expected from correlation of systematics or other systematics. And if you look, the difference between the WMAP satellite, which provides a cosmic microwave background map, and Planck, this is what they got. They got a kind of big surprise. So there was a big difference in the cosmological parameters. But if you look at the second release of the Planck project, the surprise was much smaller compared to WMAP. So if you compare now the two releases of the Planck project, so you see a big surprise. So it means that between the two releases of the same instruments, the Planck project, a lot of systematics have been interpreted and corrected, and now the results are closer to the WMAP satellite than it was in the first release. So that's the kind of interesting point. It means that with the same data, or slightly better data, you can significantly change the results if you understand better your systematics. So that's the second kind of thing that have to really to be taken into consideration very seriously. And for this, the only way, in fact, to deal with all this nonlinearity coming from the sky to the data is to have very, very well done pipeline which can reproduce by simulation the data we believe to observe. So we have to build pipeline, and the numerical simulation now becomes a very, very important part of the projects. So simulation is as important as statistical tools or anything. You have to compare the data to simulation with the best physical model we know, for instance, for the dust or for anything. So simulation is really part of the project. But when we do that, we want to do simulation, for instance, n-body simulation. And when we arrive in this new generation of projects, then we are faced with a new problem. Is how can we have 10,000 realization of an n-body simulation with 10,000 different cosmology? It's just impossible, because one n-body simulation is already taking forever. So there is a new problem which is not that we cannot do it from the theoretical point of view. We know exactly how to compute everything, but we don't know, but we don't have the time to compute it on the computer. So you have to make some approximation somewhere, and you have to control this approximation. So it can be approximation on making simulation, it can be approximation in some equations. So there is a lot of work, for instance, how to deal with covariance matrices and how to make simulation, how to make approximation on the building of covariance matrices. So that's theoretical work. There are some people also at CMU who try to learn n-body simulation and then using deep learning to reproduce many realizations of n-body simulation. That's the kind of work which is ongoing actually in astrophysics. There is also some work on the likelihood and to try to use modern tools for deriving a kind of approximate likelihood. So that's the kind of approximation that you have to deal with in the future. And now I'm going to show you the kind of data we have. So today we are already in a kind of big data regime. For instance, this is the LOFAR instruments. LOFAR instruments is the radio interferometers. So radio interferometers works with antenna, and there are antennas all around Europe. And if you look at the number of bits provided by this instrument, is something about 24 petabytes per day, and 1 petabyte per year in the archive. So we are already in this concept of big data, and you have to have a fast computer and to process with this data. When you work with the radio interferometers, what you observe, in fact, is a Fourier sampling of the object you are looking for. So each pair of telescopes provide you one point in the Fourier space. Okay, it's really very similar to MRI imaging for people who know more medical imaging. So we observe, you have really a subset observation of the Fourier space, and this is the kind of data we have. So this is the coverage in the Fourier space, and you have this part of circle because the Earth is rotating. So during the time you observe different points in Fourier space with the same pair of antenna, and this is the image you got if you take just the inverse Fourier transform of this data. And here's what the pipeline of LOFAR is providing. This is real data. This is Cygnus A image. And now we are using here more modern statistical tool to recover this image. And what you have used here is sparse recovery. So the L1 norm minimization of some coefficient in a given dictionary. So I think that many people here know what I mean. And what we got on this image now is these features. Okay? So here you could see you have much more details than here, right? With the same data. And you can even, checking at the resolution, you can even say that with the same data you have double the resolution. So this is quite impressive. You double the resolution with the same data. So, but the question was, is this true? Are these details true? But for this image, it happened that you have another observation at another wavelength, which is at a better resolution. So we could overlap what we got in color from LOFAR instruments to the very large array data, which is the contours. And we could demonstrate with real data that the sparse recovery was really recovering the resolution that was not recovered with the previous algorithm. So this is to show you that having better instrument is very important. but having better statistical tools is as well important. You can double sometimes the resolution of what you get. So to do this, for people who know a little bit sparse recovery, so you have this kind of equation to solve. You have an inverse problem, and your solution is described in the given dictionary phi. And typically, you have this kind of equation to solve. And maybe the thing that you are doing a bit differently is we have a very smart way to estimate this lambda parameter. And this is a bit technical, but it's very useful in practice. So we derive this parameter from the MAD, the median of absolute deviation of the residual at each iteration. And doing this, in fact, you have to change a little bit the equation because the noise then is not Gaussian anymore. It's correlated. So in each wavelet band, we have one lambda, but the lambda can be derived automatically. So in fact, what you minimize is this equation where you have one lambda per wavelet scale. So this is for people who know a little bit. But it happened that it's very, very efficient in practice, and we don't have to think about anymore about how to fix these lambda parameters. That's another point which is important. If you have a very, very fast and smart algorithm, but you have one or more parameters to set up, and you have to run many times in order to find what are these parameters, your algorithm is not fast anymore because you have to look at the result and to restart the algorithm with other parameters. So having an algorithm maybe which is not as fast as the fastest algorithm, but where you can directly fix the parameters in a way that you know that it will provide a good solution, that's very important in practice, especially if you have a huge amount of data and you cannot afford to process many times the data. So this is for radio astrophysics. What is radio astrophysics tomorrow? Radio astrophysics tomorrow is really the Square Kilometer Array. So now we have many, many antennas. And these projects have been started already. So there are already some data which are collected. But the full project will be only running in 2023 or 2024. So SKA is the biggest challenge in astrophysics ever. Because the pipeline will have to address more than 6 terabytes per second. So this is something very, I will say, similar to Google or this kind of thing. So it's very, very important. And at the end, you have 1 petabyte per day to store in the archive. So in practice, they are still thinking about how to build the detector. And when you have these visibilities, you have a lot of information. You could imagine to try to recover all the best resolution you can and in space and in energy or spectral dimension. So you will have for each image 50,000 per 50,000 pixels and 65,000 channels. So you could imagine that's a kind of big cube that you have to address in your computer. Or you can decide that you cannot do it at this resolution and you shrink the resolution or spatially or in frequency. That's kind of option that you have. Just to show you how difficult it is, the engineers in charge of designing the pipeline are wondering if they should work in float or double. That's the kind of question they address actually. Maybe they say, maybe you can just work with float, so we divide the memory in the computer by 2. That's the kind of thing they consider. There are other kind of projects like LSST. So this one is a US project with some team in Europe as well involved. And this is really to observe, to try to measure the dark matter. I will come later on this. And this project will start also around 2020. And it will have at the end 100 petabytes of data for 10 years. So this also is kind of a big data program. And here we have the project will make really a huge observation of the sky and make what you call the big surveys. And the best one, and I'm biased because I'm working this project, is the Euclid project. So Euclid is a space mission. It's founded already by ESA. So it's more than 220 laboratories, more than 60,000 countries, and more than 1,400 people working in this project. And the goal of this project is to measure several billion of galaxies and the shape of this galaxy, and I will come back why this shape is important, and to try to say something about the gravity, if you have to change it to go toward model of modified gravity, or if you believe that the gravity as it is defined now by the general relativity is fine. That's the kind of goal we have in this project. And we want to go to space because we want to better control the systematics. And here we are again looking for very, very fine feature. And for this, so we have this mission. It will be a 6-year mission, so we'll observe for 6 years. The launch is planned for 2021. It will be a 1.2 meters telescope in space with 4 instruments. One visible channel in optics to really measure the shape of the galaxies, and one infrared channels, and one spectrometers. We will not have the whole sky. We'll have only 15,000 square degrees of the sky, so it's a bit more than a third of the sky. So this is where we will observe, and we'll observe 1.5 billion of galaxies. And the main way to observe the data will be weak lensing. So I think everybody knows what is lensing. Is if you have some matter in space, and if you observe a galaxy, the light of this galaxy will be slightly distorted by the matter. So we will observe a bit different. The shape of the galaxy will be a bit different from the original shape. And we call it weak lensing, is because in fact the modification of the shape is very, very slight. It's only 1% of the own ellipticity of the galaxy. So here I have to amplify by more than 100 the deformation in order to be able to see it. Okay, so it's very, very small feature. So this is so why do we want to make this measurement? Because from this measurement we can build maps of dark matter. And this is very interesting because it's really an observation of the mass of the universe, but without any light emitted from this mass. It's a light emitted from background galaxies. So you observe dark matter which is here or here, but the galaxies are behind. So you reconstruct a map of what is here without any light from this part. So you don't have the bias between the light and the baryonic matter. Okay, so it's a direct measurement of the mass. So you can compare the mass that you reconstruct, for instance, to the galaxies or to the other observation, like in X-ray. And one of the very famous map of dark matter is this one is a bullet cluster. You have in blue, you have what is reconstructed from weak lensing, and in red you have what you get from X-ray data. So you see that, and if all the matter will be baryonic, so you will everything will be included in the gas because the galaxies doesn't count in terms of mass. Everything is in the mass in the gas, and the galaxies are not are collisionless. So the galaxy, when you have 2 clusters which fall, they just cross. The galaxy just cross over without any interaction. While the gas has some collision, so the gas stay here. So we see the collision of the gas, and here we have the galaxies or the mass related to the galaxies. So this image was kind of a big argument for the presence of dark matter in the universe. We can also try to count the peak in the map. If you reconstruct a map, we can count the peaks. And this peaks also is a very good indicator of how the gravity is acting in the universe. So you can count the peaks, which correspond to dark matter halos. And you can do it for different redshift or distance from Earth of the galaxies. Okay, so it's also another way to measure the gravity. So how to do that in practice? In practice, you observe images, stars, galaxies. So we have very good techniques to detecting these galaxies and making the separation between stars and galaxies. And this is typically done using deep learning technique or machine learning techniques. So we have a separation of stars and galaxies. And then we have some patches containing galaxies and some patches containing stars. And you will see that going to space is very important because that's the same image, the simulation, observed by the Hubble Space Telescope, and here observed from ground. Because of the atmosphere, So all the images are blurred by the atmosphere. So even if you have a bigger telescope, it doesn't help improving the resolution of your instrument. When you have a bigger telescope, you improve the sensitivity. So you have more photons coming to from the objects, but you don't improve the resolution. So going to space, now you can really reach the resolution related to the diameter of your telescope. So it's very important if you want to measure the shape accurately. It's very important to go to space. So the way that you do it, then we are measuring the deformation in two directions. And it's called gamma 1 and gamma 2, and we call this the shear of the galaxy. So the shear, so it can be derived from the moment of the image, and depending on the value of the shear, it corresponds to stretching in one or the other direction. So from this shear, we have direct relation from this shear. So the shear is a kind of vector field. And there is a direct relation from this vector field to the projected mass, which is called the convergence map. And the only problem is you have to deal with noise, pixelization, and the point spread function of the instrument. So if you observe a galaxies, and here's the point spread function of the instrument, that's the answer of your instrument. So if you observe a Dirac, you won't have a Dirac on your image. You will have a blurring things, which will look like that. And if you convolve this galaxy by the point spread function, this is what you observe, and then you have some noise. So somewhere you need to recover from this the shape of these galaxies. So it's a kind of deconvolution problem. And it's very difficult because you have all this problem of noise, pixelization, and everything. And also it's very difficult because the point spread function is not constant. It's varying spatially. So you have at different position of your image, you have different point spread function. And you don't know it. So it starts to be tough. But you are lucky because you observe stars. And stars, it's like a Dirac because you don't resolve stars. So each star is a kind of measurement of the point spread function of the instrument. So from these stars, we can try to assess what is the point spread function at the position of the galaxies. So it's a problem where we detect the stars, but it's an observation of stars. So it means noisy and undersampled. And from these stars, we want to find what is the point spread function at the position of the galaxies. Okay? So it's an estimation problem and interpolation problem at the same time. So this is the kind of problem you are addressing in my lab. So so you have to take into account the fact that the images are undersampled. There is a space dependency, there is a time dependency, and there is a wavelength dependency. Okay, because depending on the color of the stars, it's more red or more blue. The PSF is also varying. So all these problems have to be addressed in one unique inverse problem. And we started very slowly, only with monochromatic PSF field estimation, without taking into account the time and the wavelength dependency. And how can we do that? So we have stars in the image, and you can look at that like points in a graph. Okay? So what information we have? We can say that every point spread function should be positive. So positivity constraint is a natural constraint. We can also assume that there is a kind of low rank constraint. So it means that we can assume that each point spread function is a linear combination of few what we call eigen PSF. And we can consider also some kind of smoothness constraint on the PSF. A PSF is not a noise, so it's somewhere structures. So we can assume some constraint. And there is also a proximity constraint. So it means that if you have two stars which are very close, you can expect the point spread function to be similar. So we need to have an inverse problem which includes all these constraints all together. And as I told you, you can see this on the graph, and you can use it, the distance between stars as well, to solve the problem. So we introduce here matrix factorization, and each column here is a star, and you can decompose X equal SA, and S will be the kind of eigen PSF I was speaking about. And the A vector, the A matrix, can be again decomposed in two parts, and this part can be seen as a dictionary or a kind of harmonic analysis, but on the graph. And these are the coefficients on this graph. So you can encode a sparsity constraint or a smoothness constraint on these alpha coefficients. And you can also have a smoothness constraint on the eigenvector. So you can plug everything in one equation, and then you can solve it and get a result. So I'm not going to go into the numerical details because it's really boring. But just to show you that it works relatively well in practice. So this is a simulation of the principal function of the Euclid instrument. And you have, as a quality measurement, you have the standard deviation on the ellipticity, because this is the most important for us. And that's the kind of recovery that we have. That's a real object. That's what is recovered using kind of a state-of-the-art algorithm in the community, which is called PSFX. And this is what you have using our technique, which is called RCA. So it works better. And if you look at the error on the ellipticity, what you get here is huge. It's 1 order of magnitude better. Okay, so it's a very, very important improvement. We don't know at this stage is this improvement is significant in terms of quality on the cosmological parameters, because for this you have to process a huge simulation that we don't have this kind of simulation at this stage. But that's the kind of things you can expect to improve thanks to this kind of algorithm. Another direction that you are working, and also with Gabriel Perret who is here, is how to interpolate stars using optimal transport. So we have already 2 papers, one is accepted, one is submitted, and this is the kind of thing we are also working, and I'm going into some more details. But now, assuming that we know the principal function for each galaxy, how can we make a deconvolution? So you have Y standard deconvolution has this format. You have Y equal hx, and I told you before that the principal function is not constant, so you cannot use Fourier transform to diagonalize this operator. So h is huge, okay? And the standard way to solve this problem normally is to use some kind of constraint, and sparse recovery is one of them, which is certainly the most efficient up to now. But here, the problem is h. The problem is not the algorithm to find x. And yeah, so you can try to reduce the problem, because I told you we can detect where are stars and galaxies. So we can consider that you are only interested on galaxies. So we can not derive in Y, you can only put the stamps of each galaxies. And we don't care between 2 galaxies what is between 2 galaxies. So we shrink the problem to a more reasonable problem. And now for each galaxy, we can assume that you have the PSF with the method I showed you before. And for the galaxy, we can assume that it is spatially constant on the small galaxy. So now we have this problem to solve for each galaxy. So it can be even distributed on many computers. But when we did this, there was something which was quite interesting, is the idea that now, because we are addressing such a big data set, we can also assume that all the galaxies share the same properties. So we are deconvolving millions or billions of galaxies. So we can also assume that there are many of them are very, very similar. So you can also imagine the problem differently, and now saying that because they are very similar, you can also have a kind of low-rank minimization of the vector x, meaning that you have some kind of eigen PSF which will represent perfectly all the galaxies. So we can address in a different way the deconvolution problem because of this huge data set. So here somewhere, having a large amount of data allows us to see the problem under a different point of view. And this is kind of interesting point. And just to show you the impact of having more and more galaxies. So this is the deconvolution results, the standard deviation of the error with different SNR for the galaxies. And this is what you get if you apply sparsity independently on each galaxy. And here, if you use low-rank minimization. So here we have 100 galaxies. Now we increase to 1,000. So now we have, you see that low rank start to do almost as good as sparsity. And now if you go to 10,000 galaxies, now low rank is even closer. So you can imagine that when you have 1 billion, then we can do much better than sparsity using low rank minimization. Okay, so and this is just because they share the same properties. Next point, and this is really fresh result because I got them only half an hour ago. So my postdoc, Sam Farren, just sent me the slides, so everything was ready for today. So here we had first estimation of the point spread function, and then deconvolution. But at the position of the galaxy, we have also some information about the point spread function, because the galaxy is a convolution of the true galaxy and the point spread function. So can we use this information as well? So we have addressed the problem differently now. We say that we don't know the point spread function at the position of the galaxies. We have only a kind of first guess coming from the method I showed you before. And we can try to estimate at the same time the deconvolved image and the point spread function at the position of the galaxy. And then you can have an alternate minimization between the two. And you can try to recover the image. And this is what Sam sent me today. Is in black, we have what we have is the previous technique. Okay, so that's the error again. And in green is what you get now, re-estimating the PSF at each iteration. And in red it is what you would have if you knew perfectly the point spread function at the position of the galaxies. So we have shrink the error in a significant way between compared to what you had before. So this is kind of also something that we are going to pursue. It's quite interesting. And that's kind of images that we have. Okay, it's small galaxies, so we don't see much on that. So this is for shape measurements, galaxy deconvolution, PSF field estimation. And I told you before that when you have this shear, you can also try to reconstruct maps of dark matter. And for this, we have another source of problem is the galaxies have their own shapes, right? When you measure the ellipticity of galaxy, you have the shear of the galaxy, but you have also the original shape of the galaxy that you don't know. And you know that the shear is at maximum 1% of the ellipticity, what you call the intrinsic ellipticity of the galaxy. So here we are going to assume something else. We are going to assume that if you look at a small part of the sky, and the dark matter should be almost constant, then there is no reason why the galaxy should be oriented in the same direction. So if you look at the galaxy, one should be there, this direction, this direction. So somewhere, if you average the shear parameters, and if there is no dark matter, you should have 0 in average. But if you have some dark matter, then each galaxy is slightly sheared in one direction, and when you average the shear, you have a small bias. And it is this small bias, very noisy, that can be associated to the dark matter map. So the way we do is we cut the sky into big pixels, and each big pixel should contain at least 20 or 30 galaxies. And for each galaxy, with the techniques I showed you before, you reconstruct the shear, and you average the shear, and then you get this kind of vector field. And from this kind of vector field, then you have very straightforward equation which go from the vector field to the convergence map. Okay? So it's very easy equation, but again, I told you before, it's very noisy. You have the pixelization, and at some pixel you may have no galaxies. So you have also this problem to face, missing data. And that's an example of what is the state of the art. So you have this is a cluster of galaxies. So here we have, so in fact, all the black point you see here is a position where we have information. Okay, so we have information only at this position there. And because it's very difficult to do something, people are pixelized in a much better way in order to have galaxy everywhere. So when you do this, you lose some resolution. Okay, and if you try to invert to recover the map, you get something very bad. So you smooth with the Gaussian, and this is exactly what people are doing. You get this kind of images. here again, you can imagine an inverse problem. And then if you do that, you say that you have galaxies which are at real position. So you cannot use the FFT, but you will use an unequally spaced FFT. And you have an operator to solve, and you will add some constraint. And again, you can use sparsity. So the fact that you assume your signal to be sparse in a given dictionary, and you can, again, minimize the L1 norm of the coefficients. So we end up with what you call the glimpse algorithm. So I'm not going to the detail, but it's a proximal algorithm that's worked quite well. And this is the kind of result we have. So this is a simulation. This is where we have information. So somewhere we have only 7% of position where we have information. This is the Kaiser square, the state-of-the-art inversion. This is if you smooth it. And this is what you can recover with the glimpse algorithm. So this is a noise-free inversion. There's just the data without any noise. If you add some, so this is what you get. So we can recover this compared to this with standard techniques. So if you add noise, somewhere it blurs everything. So we can still do better, but it's not as impressive as when there is no noise. But you can clearly differentiate that there are two features in this image, while the standard techniques cannot do it. So we have applied this to real data. And here, there was a kind of controversy on this cluster. The controversy was about a dark peak, which is here, P3 prime. And one paper claimed there was a dark peak, and another paper was claiming there was no dark clump. And having a clump is quite important in terms of nature of dark matter. So somewhere, if there is a dark clump, it will be difficult to explain it with the standard model of dark matter. So this is kind of a hot topic. And so we contacted the two teams. We got their data, and we reprocessed with glimpse the two data sets. And what we got is that we could detect the peak with the two data sets, but at a very, very low significance compared to what was claimed by one of the papers. So one of the papers was claiming something like 6 sigma detection, where we were at less than 2 sigma, something like 2 sigma detection. So our conclusion was there is something at 2 sigma, but it cannot be interpreted as a dark clump because it's not really significant. And this is this was our conclusion on this paper. And the last application, it was by my colleague at UCL. They used glimpse to process the last observed data, which is the dark energy survey data. And I'm not sure you can see it very well, but this is what you have reconstructed using glimpse, and this is what has been reconstructed by Kaiser and Square, the standard technique. And you can see that you have a much, much better recovery of all the dark clump. Then for any study which will start to count the clumps and trying to compare to the cosmology, this map will be much, much better. So I will conclude here my talk. So I will say that we have fantastic new data sets that will come in the next 10 years. I can say that it will be the golden age of cosmology from 2020 to 2030 with LSST, Euclid, and SKA. So it will be very impressive. I showed you that we had two uncertainty, and there is a third one which is now coming up, which is the approximation. Another challenge is HPC. We have so much data. How to deal with such an amount of data? How can we process our smart algorithm on such an amount of data? So sometimes we may have to choose a kind of worse method just because we cannot perform the fast method, which is very frustrating if you are involved in the methods. And another issue which is important is reproducible research. We want to be able to reproduce the results, and with such an amount of data, is any other team able to reprocess the data? I'm not sure, right? Because if you need supercomputers that is available only in the consortium, it will be very difficult for a small team, for instance, to even if it has the software and the data, just to process the data again. So that's a kind of also issue that you have to think about it. And also the kind of new direction of astrophysics is maybe the future astronomer will never go for observation anymore because the data will be there acquired by LSST, Euclid, or SKA, and the astronomer will only ask for computation time to process the data. And that's the kind of proposal he will make, is just to call for computation time. So you can see a kind of shifting in the way that astronomer may have to think in the future. Thank you.
Thank you for the fascinating talk. My question is about the algorithms. So I'm more from machine learning, where we have similar types of inverse problems, but we have the property that we don't need to solve them very precisely because of statistical reasons, otherwise it's overfitting. And therefore, we use fast algorithms like stochastic gradient, etc. So my question is, in your case, do you need to have a very precise optimization? And do you use things like stochastic optimization to have fast but inaccurate solutions with big data?
So many groups are really investigating machine learning and deep learning right now, right? Especially in US, but also in Europe. Just to give you an idea how it evolves very quickly, I'm organizing every 2 years a conference in Cosmostatistics. And in 2014, I wanted to have a machine learning session, and I could not fill the session with the talk I received. So I asked some master students to give a talk, and it was very hard. In 2016, I made the same conferences, and we had 3 sessions just on machine learning, just because everybody was doing machine learning. So it's very active at this time. Machine learning, deep learning is very active. We start to see the first results, especially for classification. For instance, for strong lensing detection, deep learning beat out all the other methods. Okay, so that was the kind of challenges. For inverse problem, at this stage, I didn't see any machine learning really beating other standard techniques. But maybe in the future, the question will be differently. Maybe it's not as good, but it's faster. So that may be the kind of new way to address the problem. But at this stage, for deconvolution, I didn't see any machine learning techniques. But concerning the bias, machine learning techniques are, for the shape measurements, there is no unbiased method for measuring the shear. Mm-hmm. So some people are running huge amount of simulations, measuring the shear, and trying to compare the bias they have using the one given method and the true shear that they have put in the simulation. And then using machine learning to correct the measurement they made on the data.
Thank you.
So what is exactly the shear? So the shear is like a direction and an anisotropy, or is it something different?
The shear can be derived from the ellipticity. It's
it's basically locally you have like a small ellipsoid or something like this? Or?
Yeah, somewhere you model the galaxy as an ellipsoid,
okay.
And you can measure the ellipticity, and the shear is just related to the minor and main axis of the ellipse.
So then do you use tools like similarly to what people do in diffusion tensor imaging, for instance, in medical imaging, where they also measure anisotropy and direction to process
So I
data?
think here the difficulty is not exactly the same. The difficulty here is to have an accurate and unbiased measurement. And when I say accurate, it's extremely accurate of
input some kind of local regularity of this field or something like this, like use wavelets or whatever. And I guess people also in medical imaging, they use probably similar ideas to regularize.
You can do this for building the images, but when you want to make the power spectrum, for instance, of the shear, you don't want to make kind of nonlinear processing on the shear using regularization that you cannot reproduce properly in the simulation. But maybe there are some things to investigate in this direction, but nothing has been done up to now.
Yes, so for denoising problem, recently there has been some relatively impressive results with machine learning, but they are using very strong models on the noise. In other words, it's very strongly rely, for example, on the fact that the noise is Gaussian or whatever, and then they build a cost function based on the noise model. So I'm wondering whether in that kind of situations in cosmology, do you have really Gaussian noise model or whatever? Do you have very good model of noise that would allow to apply such things?
Yeah, I would say yes. I would say yes. It will not a wide Gaussian noise. The noise will varying spatially. But I think we can derive proper noise estimator. Yeah. Or we can derive some noise simulation which correspond to what we expect in the data. I think we should be able to do that.
So there may be things to be done.
Yeah, I believe I think there are a lot of room for doing many things, right? In machine learning only started in the field. Yeah, I told you, in 2014 there was nothing, right? So the situation is really growing exponentially, and people are investigating more and more for more and more problems how deep learning and machine learning tools can be applied for many applications. So for instance, for galaxy classification now, it's only machine learning techniques which are used. For redshift estimation, so the distance of the galaxies, it's also mainly neural network. Star galaxy classification is again neural network. So you can see neural network coming up almost everywhere. No.
When you say deep learning and things like this, it's just like classical image processing deep learning, or is there anything specific to astrophysics that you don't see everywhere? Are they just like clicking on buttons, or are they like creating new things that would be interesting outside just image processing?
I think it's more using toolbox. Yeah.
So there's no like specific.
No, I didn't see any very specific development in machine learning.
I have a kind of generic question. So there have been a lot of development in math and applied math, and leading to new way of addressing inverse problems, like of course compressed sensing and everything. And so, how much does this influence the way you create a new mission, a new detector in, say, Euclid or even before? I mean, how much of this is really influenced by the people saying, hey, now we can know these things, so maybe we should measure things a different way? Or maybe it's hard, actually, to transmit this notion to...
Yeah, so first you have to know that when you design a new space mission, it's something like 20 years before the mission arrives. So the first time I saw really impacts of algorithm to try to push a new instrument, it was the talc instrument that we did make a proposal to ESA 2 years ago, but it didn't go through, so the project will not exist. It was an annular telescope. So in fact, the idea was to have in space a 25-meter telescope. So 25-meter telescope in space is impossible, right? But if you assume an annular telescope where you have a mirror only on the border, then one engineer at CA has seen that you can build a piece of mirror that you can stack in a rocket, and you can deploy the mirror in space. And you can have it in a very robust, rigid way. So you could have a real telescope in space with a 25-meter diameter. And to show the quality that we could, the images of what you could do with this telescope, we use sparse recovery and everything. And this is the whole proposal was made using algorithm and software based on new techniques. But there was some technical, it was not software issue, it was really technical issue that the project was not mature enough for ESA to push it further. Right. So the conclusion, it happens, but it's not very often, yeah.
Okay, so maybe the next generation.
Maybe the next generation, yeah.
Okay. All right, if there are no more questions, let's thanks our speaker again.